Welcome to Demo Days Electricity and Magnetism. My name is Michelle Brasso. I teach physics and 9 through 12 science. You probably already know a lot of static and current electricity demos. Here are some of my favorites. Use a high-frequency generator, also called a Tesla coil, to differentiate between conductors and insulators and give students a shocking experience. Give your Van de Graaff machine a new hairstyle. You can also use dry erase markers to draw a face on your Van de Graaff machine, and it gives it a little bit more fun. Use fruits and vegetables to create batteries. Build a motor. Use a multimeter to plot equipotential lines. From this session, I want you to be able to bring back to your classroom a demonstration in a lab related to electromagnetism. This will show your students how we actually generate electricity, and then from there we can spin this off to electricity generation projects. As a bonus, at the end of this session, I have a Crafty circuit activity that you can do with your students that involves creating a pop-up circuit card. One of the biggest discoveries in electromagnetism was Hans Christian Ørsted's discovery that current-carrying wires affects magnetic fields. We're going to demonstrate that to our students. What you'll need is a power source. It can be one like this, or it can be some batteries in series, current-carrying wire, and compasses. This one is pretty simple to set up, but it has some interesting results that will make your students think. This one is really well suited for predict, explain, observe, explain scenarios. So we simply take the current carrying wire and lay it across the compasses. You'll notice now all of the compasses are pointing north. Once we turn on the power source, you'll see a deflection in the compass needles. So that is interesting in and of itself, that a current carrying wire affects the magnetic field around it. These compasses are really balancing two magnetic fields. We have Earth's magnetic field. We also have the magnetic field from that current carrying wire. So there's our first discovery, that a current carrying wire generates a magnetic field, and that's different than that of Earth's magnetic field. We can extend this further as a demonstration for our students by showing them what happens when we place the compass on top of the current carrying wire versus below the current carrying wire. We'll see a different result. Again, with this demonstration, we just want the current on for a moment because we don't have a load running here. Just want the current on for just a few seconds at a time. This experiment is great to show students the difference between the magnetic field's direction above the wire and below the wire. Notice how the two compasses deflect in different directions? But we'll use a different flavor of this experiment to show what happens on either side. When we place the current carrying wire in between two compasses and turn on the power, there's electricity going through here, but there's no change in the compass needle. Instead, what we need to do is suspend this wire so we can see all directions around it. In order to perform this variation of the experiment, I recommend using a retort stand with two clamps on it. We'll use a piece of cardboard that has a hole cut through it such that the wire can go straight through. We'll set the wire through the first one and use the top clamp as just a way of holding that wire in place. Next, we'll place our compasses on the cardboard, and this way we can get compasses in all directions around our wire. Now that we're all set up, we're ready to send current through the wire. Like last time, we just want the current flowing through the wire for a few seconds at a time for safety. Immediately, we see that deflection. Something you can explore with your students is the relationship between the distance of the compass and how much it deflects. So we have one close, one sort of in the middle, and one further away. When you turn on the current and it's flowing through, how much does each needle deflect relative to one another? So you see this one deflects the most, the second most, and the least. So there's definitely a relationship here between proximity and the magnetic field's strength. Hans Christian Ørsted did this demonstration in front of his class. It didn't work the first time, but eventually he did get it to work. If it doesn't work for you the first time, my recommendation would be to curate which compasses you're using. Some of mine are tossed to the side because they're not playing nice and not moving easily enough. Now we're going to move from our demonstration to the lab. So again, Ørsted proved that a current-carrying wire induced a magnetic field. We saw that when the compass needles moved. The compass needles are affected by two magnetic fields. One, the magnetic field from that current-carrying wire, and two, Earth's magnetic field. So Michael Faraday thought, if a current-carrying wire can induce a magnetic field, what about the converse? Can a magnet induce a current? And that's what we're going to explore in the lab. For this experiment, you'll need an air core solenoid, banana clip wires, and either a galvanometer, a multimeter, or a wireless current sensor. To set this one up, it's pretty simple. You can start this with a demonstration as well. I'll start here with the most basic on the galvanometer. Got this ready to look. So what I have here in my hand is a neodymium magnet, and I'm going to bring it near the air core solenoid, and you can demonstrate this to your students as well, what shows up on the galvanometer. So as we place it near the solenoid, it moves. So we've got some current flowing here. Something that your students can explore is what happens if you just place it on top. Nothing's happening on the galvanometer. What if you place it on the side? Oh, there was something for a moment, and then it changed. Let's take the magnet out. Oh, when I took the magnet out, the galvanometer perked up again. So a discovery that your students will make is that as the magnet moves, the current changes. This is actually how we produce alternating current. A magnet or a solenoid moves, and because the solenoid always opposes the motion of the magnet, we generate an alternating current. If I bring a north pole towards the solenoid, it generates a north pole here. If I move that north pole away, it generates a south pole. Am I breaking any laws with this? No, I'm not breaking any law of conservation of energy here, because the electricity that's generated, that electrical energy, comes from the work that I do to move the magnet. So we're not breaking any laws, and that's a good connection for your students to make too. Now let's get into planning this lab with your students. We have different factors that your students can change in order to determine how they affect the amount of current generated. Doing this with a galvanometer is not optimal. So it's really difficult if they're going to change some factors to get an accurate measurement on the galvanometer. In years past, I've used a multimeter with a good amount of success, but it's not my favorite, and I'll show you why. Looking at the multimeter, you can generate a current. Once students start to get into larger currents, they may have to change the settings, and they may not know how to do that just yet. So here it is on milliamps. So you can see that it's generating a current, but it's tough to track just the highest current that you're going to get here. It only samples so frequently, so you're not going to get a very accurate result. What I prefer is using the Pascal wireless current sensors because it shows you a graph over time of the current that's generated. In this experiment, you would have students change one of the variables. It could be changing the type of magnet, changing the speed of the magnet, and you don't need to know the actual speed, just maybe slow, medium, and fast. They could also change the location of the magnet, or they could change the type of solenoid that they have. You're going to see why I love these sensors so much. We're going to build a new experiment, choose this layout. I'll choose a graph here and the values here and just connect my sensor. Perfect. And now we'll select the measurement, select current. I won't move too fast, so I'll use milliamps. And then we can always adjust if need be. I like increasing the data frequency. So we're going to start this. And you can see how much the current changes. So this is with the neodymium magnet. Try to keep it roughly the same speed. So this is one of the magnets off my chalkboard, and you can wait a little bit, and then you can try another magnet. Try to keep it the same speed, and then students will see that there's quite a big difference. That first one was the neodymium magnet, the second one was a normal chalkboard magnet, and the third one was this little chalkboard magnet. Another experiment that students can do is changing the speed. So they would keep the same location and maybe go slow, get some data. We can let that sit for a moment. They can move at a moderate speed. And they don't even need to know the exact value, but then they would go faster, and they can see that that produces a greater current. They could also change the location. So the third one here, they might choose different locations. They might choose next to the solenoid, like we've been doing, and trying to keep the other variables constant. They might choose to the side of the solenoid and trying to keep that constant. So if fine here on the side is not as effective, they may choose above. They may choose in and out and make that discovery as well. So I love seeing this in graphical form. Students can fill in their data table. And again, here we're not looking for specific values. Instead, we're looking for those relationships. How does the type of magnet affect how much current is produced? How does the speed of the magnet affect how much current is produced? How does the location of the magnet's motion affect how much current is produced? And if you have different solenoids with different numbers of turns, you can also test that as well. If you want to extend this lab for your more advanced students, you can use the wireless current sensor in tandem with the wireless voltage sensor and display either graphically or numerically the voltage as the magnets moved. I love the labs and I love the demos for electromagnetism, but even more, I love the engineering challenges. Now that your students know how to generate electricity and the different factors that affect how much current is produced, let's get them building something. So in your classroom, you can have students building wind turbines or water wheels or some sort of crazy elastic potential energy contraption that generates electricity. And from there, you can measure them using the sensors or a multimeter and see which group got the highest current. It is a lot of fun. I've been doing that for years. It's a great day. Another thing that you can do is find these little motors. If you're less interested in them actually generating the most amount of current, you can get these little motors and they light up when they spin. So you can have these connected to a water wheel or to a wind turbine and just have the students generating that electricity. If you're using these, then you have no use for these big solenoids. So this is a nice budget option for your classroom. Let's make a pop-up LED card. To make these pop-up LED cards, all you need is 2 pieces of paper, one with the template printed, some glue, scissors, conductive copper tape, a few LEDs, a little button battery, and some clear tape. Optional is a paper knife. Let me interrupt myself. If you go to the virtual swag bag page, you'll get this template. You'll notice that the template actually has the letters backwards. So once you click on it, you can edit it to say whatever you want to, and it will adjust for space. And then you can just move these sections around, and you may have to duplicate them depending on how many words you have. But you have access to a template to make this nice and easy for you. So we'll start off with our back, and the back is just going to be folded in half, what they call a hamburger fold, but I think it should be called a taco fold. And our other page is going to sit on top of this. What we're going to do is just make a little slice on one end so that our battery can flip. So just about 1 inch long. Then we'll take the copper tape and we'll just lay it across here, right underneath the fold, and then a little bit lower as well. As long as your LEDs can fit across, you're in good shape. So something like that would work. Our battery is going to be placed here, and then we'll just flip that over to complete the circuit. So we can let this rest for now, and we'll work on cutting out the template. You'll notice that the template is backwards because then we can give our students instructions without having too many mistakes. So they'll cut out any area that says cut out, and then there's some areas that will say fold, do not cut. Hopefully they follow instructions there. And then when you turn this around, it will say the letters. So you can use scissors for this. You can also use a paper knife if you feel comfortable with that. You can choose to fold those fold lines before or after. And the way that this folds is that what the students see in terms of the instructions, that's the background. So this part will fold up so that they can read the letters on the opposite side. And this part will attach to the top of the backing. So it will sit something like this. And this part will align with the top. So in order to fold it, we fold these back as well near the letters, and then fold the other part upright. So now we have this template. It's ready to go. The top of this paper will match up with the top of the back, and likewise with the bottom. The air gap occurs behind the letters. So when you're gluing this, the tops will align and the bottoms will align, and then we just have that upside down. The tops will align and the bottoms will align, and then we have that air gap between them to place the LEDs. So now that we know where the letters are located, we can place the LEDs on the backing page. So with LEDs, I would recommend is decide which way you're going to have your battery. I like to have the positive side down and then the negative side on the top. So I can even leave a little note to myself, or you can have students write positive on the bottom, negative on the top. And then of course you would check that your LEDs are all working before you place them in. Here we'll just bend the legs of the LEDs, and we'll place the positive terminal on the bottom. Those will just tape down. So I want it to hide behind the letters. So F can go right about here. That's why we didn't tape them down at the start, because we want them to be hidden behind the letters. So that's where F will be. Looking pretty good. And then we'll just place an LED behind C and behind S. So they all light up, that's a good sign. I'll move the battery over for now, and then just glue this template on top. Again, the bottom aligns with the bottom, the top aligns with the top. You only see the background color in the middle. And there you go, a light up LED card.